Now we will study the next topic, integral over Roldan domain. Okay, so until now we only study integral over rectangles, but in application and in the theory of mathematics, we need to consider integral over more general sets. Suppose here is a set D. We want to and we have a function defined over D. We want to consider the integral of f over D. How to do this? Okay, so let D be a subset of Rn, and f is a function defined in D. The zero extension of f is the function denoted by fd, which is defined. You can consider this as a function defined in Rn, given when x belongs to D, fx makes sense. Therefore, we let the value of fd at this such x to be fx. And when x is not in D, fx makes no sense. But in that case, we define the value of fd at x to be 0. So this is a new function defined in the whole space Rn. Defined over the whole space Rn. Of course, you can also take a rectangle containing D if D is bounded. If D is bounded, you can take a rectangle containing D, and then you can consider this fd as a function defined over the rectangle. But we don't take this notation. Okay, we simply regard the zero extension to be defined over the whole space Rn. Okay. Now we have a very important lemma, which will enable us to define the integral of f over any subset D. So this is a lemma. I and J are rectangle, and J is contained in I. And f is a function defined over J. Then f is integrable over J if and only if the zero extension of f, that is fj in our notation, that is D, take the D to be J. So the zero extension of f is fj. Okay, so the zero extension is integral over I. And in this case, the integral of f over J, maybe I will write in red. The integral of f over J equals the integral of the zero extension over I. So let's draw the picture. So we have two rectangles. This is J, and we have a larger rectangle containing J, I. So f is integrable over the smaller rectangle if and only if the extension, the zero extension of f is integrable over the larger rectangle. And in this case, the integral are equal. The integral of f over J equals the integral of the zero extension over I. Okay, so this is the lemma. So how to prove this lemma? I don't know whether I have enough space in this page. Maybe I move to next page. So I need to draw the picture again. So this is J, this is I. So proof. Suppose I is a rectangle which edges A1, B1, AN, BN. And J is also a rectangle. J is alpha 1, beta 1, alpha n, beta n. So this is A1, B1. This is A2, B2. This is alpha 1, beta 1. This is alpha 2, beta 2. Okay? So Pi is Ai, alpha I, beta I, Bi. And this is the partition of the ith edge of the rectangle I. Okay? For example, in this picture, the horizontal points here, this is P1, and the vertical points here, alpha 2, A2, alpha 2, beta 2, B2 is P2. For every I from 1 to n, we take the Pi, define the Pi in this way. Then P equal P1, Pn is a partition of I. And for every rectangle in this partition, for J in this partition, J start, because the symbol J we already used to denote the given rectangle. So we denote rectangles in the partition P by J start. So if J start is not J, then we see that the zero extension of F is 0, 1 J start. Okay, let's complete the partition. The partition is given here. Okay, by the red segment. Then the J star is here. The J star, if J star is here, that is J star is not the rectangle J, then Fj, the zero extension of F outside J is 0. So Fj is 0 on such J start. Therefore, Fj is integrable in this J start, because in J start it is a constant function, identically 0. Therefore, it is integrable. And the integral of Fj is 0. And if J star is J, then if J star is J, then Fj is precisely F. So Fj integrable over the I if and only if Fj is integrable over Rj. Okay, because we have a result. We proved a result in the last lecture that the rectangle I has a partition into some smaller rectangle. Then F is integrable over I if and only if F is integrable over every subrectangle. But now we know that Fj automatically integrable over all the rectangle, all the subrectangle except the rectangle J. So this means that f is integrable over I if and only if f is integrable over j. Fj is integrable over I if and only if fj is integrable over j. But in the rectangle j, fj is precisely f. So this means that f is integrable over I if and only if fj, the general extension of f outside j, denoted by fj is integrable over I if and only if f is integrable over j. So this solves the integrability problem of this lemma. Moreover, the integral fj is the sum of j star belongs to the partition fj over the j star. But all the integral of fj over j star are 0 except when j star is j. So this gives us. But over the rectangle j, fj is precisely f. Therefore, this equals the integral of f over j. So this completes the proof of our lemma. Okay. So using this lemma, we can define the integral over any bounded subset. So we have definition. Suppose D is a bounded subset. F is a bounded function over D. So here is D, and we have a function f defined over D. Now, if there is a rectangle I containing D, such that the general extension of f outside D is integrable over the rectangle I. That is, we have a rectangle I, such that the general extension of f is integrable over I. Then we say f is integrable over D, denoted by f rd. And the integral of f over D is defined to be the general extension, the integral of the general extension over the rectangle containing D. So this is the definition of integrability of a function defined over a general subset